Greetings, everybody. Welcome back to the Enterprise IT Track. My name's Brian Rice. I work for AWS as Product Marketing Manager for RDS. And I have the distinct privilege of introducing our next speaker. If you were at Werner's keynote this morning, you recall that he highlighted the extent to which Netflix has for a long time driven innovation on our platform. And we are endlessly humbled by what they achieve, and we're so proud to be able to support it. Today, we're joined by Yury-Izrailevsky, who is VP of Cloud and Platform Engineering at Netflix. And he's going to talk with us today about a topic near and dear to my heart, what enterprises can learn from Netflix. Let's give a big hand to our speaker.
Well, can you hear me okay? A little loud. Good afternoon, everyone. Thank you, Brian, for the introduction. And today I'll talk about some of the things that we've learned as we became a cloud-native company. So our journey to the cloud at Netflix began about 5 years ago in August of 2008, during the Beijing Olympics, actually. And at that time, we experienced a major database corruption. And for 3 days, we could not ship DVDs to our customers. So this was a very costly and embarrassing outage. But at least it was mitigated by the fact that customers could view DVDs that they had at hand. And at that time, we were just beginning to deploy our streaming service. And we quickly realized that a similar kind of outage in our streaming product would be totally devastating to our customers and to us as a business. And that's when we decided that we would move away from vertically scaled single points of failure in the data center, like relational databases, and towards highly reliable, horizontally scalable distributed systems in the cloud. And as we moved into the cloud over the next few years, we focused on the following 3 priorities: scalability, performance, and availability. So let's start by talking about scalability. So as you can see in this graph, since the beginning of 2009, our streaming usage has increased by more than 100 times. So, for example, over the past quarter, we've streamed 5 billion of hours to 40 million customers all over the world. And supporting that kind of growth would be virtually impossible if we were running it on-premise. You know, we simply would not be able to rack up the servers and provision the colo capacity fast enough. And in the cloud, we're basically getting all of that scalability for free. It takes us just a few minutes to spin up thousands of servers. And we can also do it because we don't have long provisioning times. We can do it without running huge capacity buffers and just pay for what we use. And benefits of the cloud, scalability in the cloud, become even more evident if you look at our global expansion. So for a long time, we were a US-only company. And then we launched in Canada and in Latin America. And we were supporting all of those customers from our US cloud region in Virginia. And then in January of last year, we launched in Europe for the first time. In the UK, Ireland, the Nordics, now the Netherlands. And in order to give our European customers low latency interactive experience, we launched the second cloud region in Ireland. And we're synchronizing the 2 regions by asynchronously replicating data using Cassandra. So spinning up a new data center in a different territory would take us many months, tens of millions of dollars. And it would be a huge upfront investment because we wouldn't know how fast we would grow. We would have to go conservative, and then we would gradually grow into that capacity. In the cloud, we could just spin up all of that basic capacity in a matter of a few days. And we could go with a really tiny footprint in the beginning because we didn't have any customers to begin with, and then gradually spin it up as our traffic increased. So today, we operate out of 3 cloud regions. And as we continue to expand into new markets and territories and become a truly global company, we have the benefit of relying on multiple AWS regions throughout the world to give our customers great interactive experience no matter where they are. Now let's talk about performance. So as I talk to my colleagues in different companies that are thinking about moving into the cloud, a comment that I often hear is, sure, cloud is great, it's very scalable, but it's just way too expensive. We simply cannot afford it. Well, in fact, as Netflix moved into the cloud, our cost per streaming start has decreased by 87%. We're paying per streaming start 1/8 of what we used to pay in the data center. So what is it about the cloud that makes it so cost effective? And there are several big factors. One is the economy of scale. Netflix is a pretty popular service. We use a lot of resources, tens of thousands of servers, petabytes of storage. But if you compare it to the total amount of resources used by the hundreds of thousands of AWS customers around the world, we're a really small fish in a big pond. Well, I don't know, maybe we're not a small fish, we're a medium-sized fish, but it is a really, really big pond. And Amazon can really leverage that economy of scale to provision hardware and colo resources more cost effectively, and then spread the cost of software development and operations over that large customer base. So they can operate this high volume, low margin service and pass those savings back to us as customers. And of course, the second factor is the elasticity of the cloud. As I mentioned, for the Netflix streaming product, which is going through this explosive growth, it's really helpful to be able to grow without running those huge capacity buffers and just pay for what we use. And elasticity helps us as we grow month after month, year after year, but it even helps us throughout the day. If you think about it, Netflix usage is very cyclical. Most customers tend to watch Netflix in the evening. It tends to be between 7 and 8 o'clock p.m. in each local region. And then hardly anybody watches at 4 o'clock in the morning. So by auto-scaling our capacity, automatically growing and shrinking the sizes of our clusters, as our traffic grows and shrinks, we can be even more effective. So now let's talk about availability. At Netflix, our goal is to build world's best streaming product. And it takes a lot of different things. Great UI, personalization, a deep content catalog, supporting lots of devices. But at the very end of the day, the service just has to work. Just think of lights coming on when you flip that switch, or your TV channels coming up when you turn on that cable box. And we've set a very aggressive goal of 4 nines of availability, which basically means that we cannot be down for more than 30 seconds at any given week at peak traffic time. Well, that's a pretty aggressive goal. How have we done historically against that goal? So as you can see from this graph that tracks 13-week moving average for our streaming uptime, the overall trend is upward. In fact, we've added a full 9 of uptime to our availability over the past couple of years. But this has not been all smooth sailing. We've hit some rough patches along the way. For example, as you can see, there's a big dip in availability as a result of an outage that we experienced last December that was caused by an ELB failure in US East Cloud region. But we've learned from that failure, and as a result, we've re-architected our systems to support cross-regional failover. So if something like this were to happen again, we would be able to survive it without impacting our customers. In a large distributed system with lots of components, failures are inevitable. But the cloud is about building highly fault-tolerant systems out of unreliable but redundant components. So we can learn from this outage and other outages, and we can build reliable system despite some of those failures. And in fact, during that time, there have been a number of AWS failures that we were able to survive without impacting our customers. So clearly, cloud provides lots of benefits: scalability, performance, and availability. But not every cloud configuration offers the same degree of benefits. For example, you could go for the easy way and just take your data center capacity and forklift it into the cloud and just plop it into EC2. And it would probably be the easiest way, but you would likely end up moving most of your problems and limitations of the data center along into the cloud. So at Netflix, we decided to go the cloud-native way. And we've built most of our systems in the cloud from the ground up. And while it provided us the most benefits in the long run, it was a lot of really, really hard work. We had to re-architect most of our systems, like moving from relational databases into Cassandra. We had to develop a new security model, relying on AWS security groups, identity and access management, and cloud HSM, among other things. We've embraced a new operational model, switching over to DevOps. And we've even made some organizational changes so that we can operate more effectively in the cloud. So let's talk about some of these changes in more detail. So back in the data center, most of the components and services making up the Netflix product were consolidated in a single Java app called Java Web. And this monolithic app approach had some advantages. For example, latency was pretty good because components could efficiently talk to each other because they were running on the same box. And also scaling the service up was pretty straightforward as well. You just add more Java web servers and you load balance across all of them. But despite some advantages, this consolidated monolithic app approach had two major drawbacks. So one was reliability was not great. Because all of these components were sharing resources on the same box, failure in one of them was likely to cause system downtime across the entire application. And the second problem was agility was not great. Because all of those components and services were basically consolidated into a single application, various development teams contributing to those had to closely coordinate if they wanted to make any changes. So releases required lots of coordination. And the best that we could do is release once every 2 weeks. And if any of the components had any problems, everyone was held back. So Netflix is in a very competitive marketplace. And in order for us to succeed in the long run, we really have to iterate quickly and innovate and make changes all the time. So this bi-weekly release schedule was just not going to cut it for us in the long run. So in the cloud, we've moved to a service-based architecture where each component and service operates in their own separate cluster, and then they talk to each other through RESTful interfaces. And we have hundreds and hundreds of components, applications running side by side. I think we have close to 500 or 600 at this point. So right away, this allowed us to move a lot faster because all of these different components could be released on their own schedules. And teams would have total power to decide how quickly to release and how to proceed. And some more stable ones would not change that often at all, and others would go through a continuous release cycle where changes would be made every week and sometimes several times a day. So what about reliability? And the truth is that even though all of those components are not running on the same box, there are still dependencies. And cascading failures can still happen. So consider a typical example. A while back, we had an issue where there was a spike in SimpleDB 503 returns. And that impacted the instant queue service, and that brought down the API. And as a result, some of our customers could not stream on Netflix. So this is a simple example of a cascading failure affecting 3 components in the cloud. So as I mentioned, we have more than 500 components running side by side. And if we depend on the availability of each and every one of them for the whole system to operate, and let's say the availability of each one is 99%, the combined availability of the system would be 99% to the power of 500, 0.6%. Basically, the system would always be down. So we've got to do a little better than that. So somehow we have to develop architecture that can survive the failure of one or several of its components without bringing the whole system down. And there are really two strategies that can help us do that. One is graceful degradation, and the other one is redundancy. So graceful degradation basically means that if one of your dependencies fails, rather than bringing the whole system down, you simply cut off that dependency and you continue operating in degraded mode. So for example, if a movie personalization service that populates the top 10 row for the customers fails, we simply drop that row and we show popular titles instead, while the rest of the system operates as usual. And of course, redundancy at all levels is really critical. For example, we deploy all of our 500 plus applications across 3 different availability zones in each region. So if one of the zones goes down, we can continue serving customers from the other 2. And as I've mentioned, we now also support cross-regional active-active redundancy architecture, where in a stable state in the US, for example, East Coast customers are served out of the Virginia cloud region, and West Coast customers are routed to Oregon. But if one of those regions fails, we simply spin up additional capacity in the other one, and we fail them over. And just as redundancy is important to improve and support the availability of our services, it's even more important to ensure the consistency and the durability of our data. So as we move to the cloud, we've adopted Cassandra, where each data element is replicated across 3 different availability zones in each cloud region to protect us against hardware failures. And to protect us against logical failures like database corruptions or software bugs or operator errors, we generate regular snapshots of all of our Cassandra data into S3. And then to protect us against catastrophic failures like natural disasters or system-wide security breaches, we generate a secondary snapshot of all of our data, and we store it in a different cloud region in S3, as well as we store another copy with a different cloud vendor. So we have several different levels of redundancy to ensure the availability and reliability of our data. But just designing fault-tolerant systems is not enough. We constantly have to test our ability to survive those failures. You know, imagine getting a flat tire. You might have a spare in your trunk, but is it inflated? And do you remember how to change it? So one way to make sure is once a week you poke a hole in your tire and you go through the drill. And this is exactly the approach that we used when developed the Chaos Monkey, which basically goes through and it randomly terminates production instances just to test our ability to survive those kinds of failures. We also have the Latency Monkey that injects additional network latency to test our graceful degradation across components. We have Chaos Gorilla, which tests our zone failover, and now that we support cross-regional failover, we also have the Chaos Con. And we've developed a number of other various monkeys, like the Security Monkey, the Conformity Monkey, the Janitor Monkey. So now we have the whole Simian army of monkey tools to help us ensure our reliability and availability in the cloud. So the Simian army has been extremely successful in our efforts. So last year we've open sourced it. And this project has been getting a lot of traction across the community, and we've been getting a lot of contributions. And in fact, this is just one of 35 different projects that Netflix has open sourced, and you can find all the details at netflix.github.com. And together they comprise our cloud infrastructure platform that basically the sets of tools and services that allows us to build cloud native applications easily. So a lot of you guys have seen these tools and services and have started to use them and are already contributing to them, which is great. And I hope that we can continue to collaborate and move this program forward. Let's talk a little bit about operations. So in the data center, we had a centralized operations team, the NOC, which was responsible for managing data center-based capacity and then operating those bi-weekly releases. So in the cloud, we've moved to this distributed microservices architecture where each development team is fully responsible for the development, deployment, and the release schedule for their components. And there is no centralized coordination whatsoever. And just as we changed the process how we operate, we also changed the mechanism. So in the data center, we used to rely on rolling pushes of configuration to running instances. We'll just take an instance out of the load balancer rotation, we would upgrade the version of the software, and then we would put it back in. And this, binary update approach worked fine, but as we continued to grow into hundreds and thousands of instances, it became virtually impossible to keep the releases consistent. We would end up with a production cluster that runs multiple versions of our software. And this problem, we would call it versionitis. And in the cloud, we moved to a completely new deployment model where each time we release a new version of any application, we bake a new AMI for it. And then we just spin up a brand new cluster off of that machine image. And that guarantees that the entire deployment, hundreds, thousands of instances, is consistent. So that helped us cure versionitis, and it also enables us to do things like red flag deployments, where whenever we launch a new version of application, we spin up two clusters side by side, one running the old code and one running the new. And then we start to gradually shift the load from the old to the new while keeping the old one fully operational. And then if we encounter any problems whatsoever with the new code, we can instantaneously shift the traffic back to the old one. And this has been tremendously helpful in us being able to mitigate any problems with new code pushes. And this kind of approach is only possible in the cloud, where you can basically double your production capacity for a short period of time and then spin it back down after you no longer need it. Now let's talk a little bit about some of the changes that we've made to our organizational structure. So back in the data center, we had IT operations team responsible for managing our hardware budget and then allocating capacity and approving upgrades for the various development projects. And then as we moved into the cloud, we've shifted that responsibility over to the development teams. So each development team is fully responsible for the capacity. They can go and allocate whatever AWS resources they need through self-service tools, and there is no centralized approvals, there is no centralized coordination. We do focus, though, on visibility and monitoring, and we also develop efficiency tools that allow us to spot problems quickly and address them. On the operational side, in the data center, as I mentioned earlier, we had the NOC team that was coordinating releases for everyone. And then as we moved to the cloud, we've disbanded the NOC. And then we moved to the distributed DevOps model, where each team is responsible for the operations of their components, and there's no centralized gating, centralized coordination. And then we also have a team of site reliability engineers who build operational tools, and then they also maintain and share best practices across the entire organization. Back in the data center, all of our data, all of our production tables were stored in a handful of large Oracle databases. And we had a pretty sizable DBA team that was managing them. And then as we moved into the cloud, we've denormalized our data model. So now we have dozens, perhaps close to 100 different Cassandra clusters, big and small. And then we have Java and DevOps engineers who support and configure and maintain those Cassandra clusters. And finally, on the BI side, in the data center, we used to store all of our analytical data in relational databases, Oracle and Teradata, and then we would have analysts running SQL queries against them. And as we moved into the cloud and our data volumes grew into petabytes, we moved the majority of our warehouse into the cloud to Hadoop, running on top of EMR. And we have software engineers that build ETL for the data warehouse using Pig and Python, and sometimes Java and Hive as well. So whenever you consider a big technology change, like moving to the cloud, it always helps to do a pilot project first, just to become familiar with the environment and to kick the tires a little bit. So why not start with the jobs page? You know, it's a pretty simple project, doesn't require a lot of scale, not too many pages there. So practically, it's a good one, but it's also very important symbolically because it'll emphasize all the different skill set that you'll need to bring into your organization as you move into the cloud, whether you develop it internally or you hire for it externally. And to summarize, our goal at Netflix is to build world's best streaming product. But to make it happen, we need to solve all of those hard problems of scalability, performance, and availability. The same set of challenges that all of you guys are working on in your own companies. Amazon provides us with a great set of foundational cloud building blocks that we can stack together and try to solve those problems. But you know, we're still fairly early on in this cloud thing, and we have a lot to learn. So I hope that we can all work together and collaborate on things like the Netflix open source. And together we can solve all of those technical problems and build systems that are highly reliable, very efficient, and infinitely scalable. Well, that's all I had. I figured we'd just go into questions.